Hello, this is Will Suter for AZO Nano, and we're here with Thomas from Bruker. He's going to tell us about the Innova-IRIS AFM-Raman system.
Okay, yeah, so what we have here seeing at the nanoscale is a full combined AFM-Raman system actually. So it's a system that does correlated AFM-Raman studies where you get combined, co-located, correlated data. It also does tip-enhanced Raman spectroscopy, TERS, that's very much of interest at the moment. So it consists of the Innova Research AFM on one end here, the AFM-Raman confocal microscope on the other end. The Innova is a research AFM system. It's a very high resolution AFM. It does atomic resolution routinely. A lot of our customers really buy it for that reason actually. Now, you might think, why atomic resolution? You don't really need that typically in your AFM-Raman studies. But what you do need is a very stable AFM. And so that's really what that delivers in this context. On the other hand, you have the AFM-Envia, a very high efficiency Raman system, which is also very important for these combined studies where you're looking at very small samples, where you have very few oscillators contributing to the signal. These systems are joined together in hardware and in software to create the overall system. You see part of the hardware here. There's this optical arm that's coming out of the microscope, reaching into the AFM, and correspondingly there is the AFM head that allows this arm to come in. And we've really jointly developed this and in very close collaboration with Reneshaw as actually a very flexible system. This AFM head is actually optically very open, so open that it provides simultaneous access from the top and from the front. And you can see that very easily in the video views. We're here where we have a video view top down onto the tip sample junction, and simultaneously one on access with Raman from the front onto that same tip sample junction. And so one thing that this does is it allows you to align the tip, Raman, and sample much more easily. And so having developed this really jointly with Reneshaw as a very flexible system, one thing we have been doing now is a lot of applications work. We have several of these systems permanently installed in our offices and actually in the Reneshaw offices as well as the Bruker Nano offices, and are using them now permanently for applications work and for demonstrations. We have one example here of applications work we've done where we've looked at graphene. So we have an AFM image here of graphene where we see that very fine detail, topographic detail that you can see with an AFM image typically, and you see very fine detail of what these flakes look like. And we have a corresponding Raman image over here, displayed over here. So really what we did there is we obtained data from the same graphene flakes, and we obtained a complete hyperspectral data cube on the Raman side and analyzed this here to show the variation in electronic properties here. AFM, very good at giving you a very high spatial resolution topographic information. The one thing AFM is lacking a bit is the electronic structure, electronic state information that Raman gives you so readily, and thereby complementing the AFM. So we've taken our hyperspectral data cube here, and what we're doing is looking at the width of the 2D band, and that is telling us about single versus double layer regions on our sample here. That's shown in these green and purple regions here that have different spectral signature in the 2D band. We're now in a position where we can correlate that with a much finer AFM data and correlate that with very detailed information of what these flakes look like or what topographic defects they may actually have that we can actually see in real space. And so this is the kind of thing we can only do by really correlating the information and by combining it, looking at the same spot with AFM and Raman. Now I mentioned before that another thing that this system does is tip-enhanced Raman spectroscopy, TERS, something else very much of interest. And so I have an example of that over here on the other monitor, where we've taken data on a thin molecular film on a sample. And so what we've done here is we've obtained a spectrum, and we're able to perfectly assign that spectrum to the molecular species of interest. And then we've moved the tip by a very small amount, by only 60 nanometers up, and we see that the spectrum completely disappears. We see in fact that when we look at the spot size normalized enhancement factor, it's more than 10 to the power of 7, a very large enhancement factor in this tip-enhanced surface Raman spectroscopy. That's not just nice, that's actually very important. And in TERS, there is always the danger of artifacts. You can have multiple scattering events just in the far field, giving you signal modifications. Those are weaker signal modifications. They don't give you the desired sensitivity and spatial resolution. So you want to look for this very strong enhancement for small tip movements. And so that's what we proved in this case that we have. And so doing this sort of work allows us, together with really this flexible system, it allows us really actually to optimize the system for the application. We have a very flexible optical axis here on the AFM side, as well as the Raman optical arm has a lot of degrees of freedom. So one thing you might notice here among the degrees of freedom is that this objective that brings in the Raman excitation and that collects the light is at an angle here to the vertical. And so there's a question actually, what is the optimum angle for tip-enhanced Raman? You might notice that this is about a 60-degree angle to the vertical. When you look at the literature, you see clear evidence that you want to have actually such an angle. I've taken here a graph from a publication where, in this case, it was a simulation that was done that essentially showed that when you look at this angular dependence of the efficiency of the enhancement, you really want to be somewhere between 45 and 90 degrees. With this objective angle. And so this is essentially what we've done with our flexible system here to implement that. And this is not just due to the fact that the tip from the AFM will shadow your light that might come in vertically. It's also due to polarization. The E field in the tip sample junction is essentially vertical. So you want to couple into that with light, with far field light that can deliver a vertical polarization, which is essentially light that's traveling close to horizontal. Now, if this is true, then this also means that there should be a strong polarization dependence in the TERS signal. And so this is something else you may want to verify to see that you have a very well working TERS system. This is something we have actually done here, where we looked at P versus S polarization in the plane of incidence. So this is essentially corresponds to vertical versus horizontal polarization. And looking at the scales on this graph, you see essentially a factor of 10 difference in the signals. So a very strong polarization dependence, again telling us that there's really a near field effect operating here, and we're doing TERS. There's a final third check you want to do really if you want to have an optimized system for TERS, which is ultimately, really, in your TERS system, you want to be imaging and take advantage of the high spatial resolution laterally. And so this is something else we have done, where we have gone onto this molecular layer and looked at the signal at a number of locations. And so, as we can see on this graph over here, we have offset the tip by a very small amount, less than 90 nanometers to the side, from the blue to the green spot here. And what we have obtained is on the blue spot, the blue spectrum, and on the green spot, the green spectrum, where the spectrum has essentially gone away. Now, this could have a number of origins when the spectrum disappears like that. Maybe you have a very inefficient system and you have essentially hammered the surface with photons, you have bleached the sample, and that's why the spectrum went away. Or maybe your AFM is very unstable and has drifted all over the place. Or maybe the AFM is mechanically unstable, has vibrated and has flattened the tip, and the tip enhancement has disappeared for that reason. And so you check that by going back to the original spot and see that the spectrum reappears. And so that's what we've done here, where you see the red spectrum here taken again at the initial location is perfectly overlaid with the blue one, so telling us that everything is stable enough and the spectrum is still there at the original location. And so we really are doing tip-enhanced Raman spectroscopy in this case, and the system is actually very optimized for that.
Okay. Thank you very much, Thomas, for telling us about this AFM-Raman system from Bruker.
Thank you.